Okay. Right. And we continue with lecture number 4 by Sam Grushevsky.
Thank you. I am impressed you're still here. This is good. So I do want to show some of the ideas of Krichever's proof of characterization of Jacobians by a flex line of a Kuma variety tomorrow, and this will take all of tomorrow. What this means is today I have to do everything else, and there is quite a bit of everything else that's left before that. So this means the number of proofs today will be, well, convergent to 0, maybe 0. The number of mistakes will hopefully not be convergent to infinity, but may approach.
Recording in progress.
It's very good at that. So the previous comments were off the record. Good. So in particular, if you look around the audience, I think every senior mathematician you see in the audience probably knows the material better than me. So if you have questions, ask them. I can try. On the other hand, those of you who do know this much better than me, and that's number, don't hesitate to correct me. So the plan for today is to do two things. We want to talk more about the Baker-Chiesa functions in this story, and I want to try to explain not the proofs, no, but some of the ideas and why you might care in the context that we're doing. And second, I want to take flexes of Kuma varieties, which we described geometrically last time, and I want to show to you that this gives you a differential equation satisfied by the theta function. So we'll finally see the same differential equation in two different ways. This will be called the KP equation, Kadamtsev-Petriashvili equation. This is the goal. This will take effort. Okay. If I lie very badly, do stop me. So I want to remind you about the Baker-Chiesa functions. So they were considered by Chiesa in less generality. And I want to write a slightly more general statement than I wrote last time. So hopefully, while you were hiking the Great Wall yesterday, you were thinking about Baker-Chiesa functions, so they're now much more familiar. But the statement is as follows. You have a curve C, you have a point P, you have K inverse is a local coordinate on C at P. So K of P is equal to infinity, which is very convenient in many ways. And then last time I said, well, we'll have one parameter x, right? But now I'll take a whole sequence of parameters, t1, t2, t3, complex parameters. And I'll take d to be a divisor, a degree d divisor, a degree g, sorry, divisor on C. And I want it to be general in terms of Riemann rock. So the dimension of the space of sections is as expected. Okay. Then there exists unique Baker-Chiesa function psi, which is psi is now of t1, t2, all this stuff, c, p, k. And what this is a function. And let's maybe put a node here, because I think I'll be confused very quickly. So P node is this marked point, right? Which sadly plays a very different role from P1, Pg, but I'm suffering from lack of letters. So this is a function, a meromorphic function on C minus P node with simple poles at P1, Pj, holomorphic elsewhere, and such that the behavior as I approach P node is prescribed by saying that the limit is a function on C in minus P node, so it's a function of P. So this is a function of P. So that's a function of P. I'll try not to write P too much. So the limit as p approaches p naught of psi, all the data of p, well, this is not going to exist. This is an essential singularity. So I now want to cancel by saying that if I take the exponential, and before I was taking exponential of kx, so my x is t1. So now I want to take the sum of k to the I, ti, I goes from 1 to infinity, is 1. Okay? What's the difference between what I did today and last time is I allowed many, many more, infinitely many terms in the expansion. You probably would worry that somehow the way I was writing psi in the first lecture, which so far had nothing to do with this, by the way, right? I was writing psi as a series in k inverse. And now I'm taking exponentials of a series in k. So can I really multiply? So notice this is okay, right? I start with ki equal to 1. So this is a well-defined object, right? In each degree, I know exactly how to compute this. This is perfectly fine. And this is a well-defined condition. So this is the statement. The uniqueness I certainly did not prove last time, and I will not prove it. Okay, and you should read the original papers. There are many proofs in the classical literature. There are better proofs. But I want to show existence. So the way you prove existence of this thing, well, you can do it by pure thought. Maybe you say something about infinite Grassmannians. But there is an explicit way to do this. And the explicit way to do this, I'll just write a formula for you. So I want to write psi of all the data of p is going to be the integral, not from p naught, I probably wrote p naught here last time, this was a mistake, of, did I make a mistake already? We're good? Huh? Okay. Oh, please. Yes. Good. Please continue. This is great. So, and then I'm going to integrate T I omega I, Ti omega I, up to the point T, theta of P plus sum, yeah? Huh? Ah. Sorry. I said exponent and then I was distracted. Thank you. Okay. So what is roughly this formula? So this formula is roughly the following. I should tell you what omega I is. Omega I is a differential, meromorphic differential on C with an ith order pole at P naught and all A periods 0. Okay. Ui is an element in C to the G. This is the integrals of omega I over the B periods. So it's a vector of B periods. Okay, P is my point, so that's a function of P. By writing this, I mean that P is a function on, I am mapping P to its Jacobian, Z is D. Okay? Z is D as a point on the Jacobian. And maybe minus D, the way of writing things. Okay? Let me make some comments about this. Yes? I didn't tell you what the lower limit in the integral is. This is one of the comments, but this is not the first comment. Okay? So I wrote some expression here black box. And I claim that this has the right properties, right? So first of all, I'd like to claim that this has the correct behavior as P approaches P naught, okay? What matters for that? From the point of view of this function, P naught is nothing special, right? There is nothing special about P naught. So this is basically a holomorphic function of P naught. That P naught, this is just a constant. I can, this gadget here, I can just evaluate at P naught, I get something. So I better, of course, I'm missing Ki. Now I think I'm good. Okay. So I'm prescribing, so this is just the exponential behavior at, no, I was good, sorry. So this guy has a divergence, right, at the point P naught. So when I start, when the point P here approaches P naught, this is going to diverge. The integral of this is going to diverge as K inverse, right? Maybe I'm missing some I or I factorial. We're not going to worry about that, okay? So this is what gives me the divergent part. So if I'm approaching the point P, the differential omega I has an i's order pole at P. So the integral will diverge with an I minus first order pole. And the i's are mislabeled, but otherwise we're good. Thank you. As what? K to the I. D of K to the I minus 1, I think. That's what I really want, okay? So what is the fight about here? So I want this exponential to precisely mimic that. So if I'm integrating as K approaches infinity, this gadget, I'm supposed to be getting that, okay? Whether or not I made a mistake of not dividing by I or writing the wrong power, that's what it should be, yeah?
No, but the point is it should not have, the singular term should be just K to the I minus 2 dk without other terms. Because that gives you a connection between K, choice of state, and the choice of omega.
Okay, so let's do this honestly. So what I want is I want the integral of omega I as K approaches infinity to behave like K to the I, right? That's what I want. So this means I can differentiate K to the I. No, I don't need to say anything like that. I can just try to take a formula.
So for example, you cannot take K to the I plus K to the I minus 1.
So what the discussion here is about, I said this is a differential with a nice order pole. This is of course incorrect because you have to prescribe what the pole is going to look like. And the pole has to look like that. And for the pole to look like that, you see that omega I has to behave like the derivative of this guy. Okay, that's a prescription of what omega I looks like. So omega I is d of K to the I.
So K to the I plus O of 1, right? Plus O of 1.
Yeah, I mean, this is holomorphic. Okay. So let's go back to this. So if I want to tell you a meromorphic differential on the Riemann surface, I can say its A periods are going to be 0. That is fine. But then I have to tell you what the singular parts are. If I told you the singular parts and that the A periods are 0, this defines a differential uniquely because the difference will be a holomorphic differential with all A periods 0. This tells me precisely what the singular part is going to be. If I take the singular part to be d of Ki, this is what this says, then if I integrate this as P approaches the point P naught, if the coordinate goes to K, then I'm going to get precisely K to the I times Ti. Fair enough? The fact that this is a correct formula is far from obvious. I've written it as an ansatz. There is something weird happening here. I'm saying A periods, B periods. I'm making a bunch of choices here, right? Because my curve does not come with a natural choice of an A and B periods. But the theta function that I've written for you is also dependent on a choice of a period matrix. So I'm choosing a period matrix. So to prove that this formula has any chance of being correct, you better check that what I've written here does not depend on the choice of A and B cycles. This is not a computation I'm going to do, but it's possible to rather easily compute Hallis transforms, and it's possible to rather easily compute Hallis transforms. Once you are done with that, this is a formula that will define a function that has this singular part at this should be, provided that what I wrote is, sorry, yeah, so Andrei is also right. If I knew uniqueness already, and if this formula has the correct expansion for some choice of the A and B periods, then of course this must be independent of the choice in the A and B periods. Yes. But since I'm not proving uniqueness, and proving uniqueness I think is harder than just checking by hand that this is independent of the choices. Okay, and this will have poles precisely when P is one of the points P1, Pg. Okay, the uniqueness you have to prove. And I'm not going that way. So of course you are going to take a ratio. Of course this will cancel the exponential singularity, but this will do nothing with the zeros of this function, right? And of course you don't know the function looks like that. So you have to do something. And I'm not going that way. Okay. Why?
So what is the analytic condition? So this sum k to the iti should be an entire function. Is that the assumption under which
this is a let me make two more comments. Okay. One of them is I didn't write where I start integrating from, right? And you cannot integrate from P naught. This will diverge. So this means that this integral is defined up to a choice of a start of the point of integration, right? What point should I choose? Well, I want the normalization to be 1. If I believe, and you should believe that this behaves exactly like that, then I have not found for you the correct function, right? Because if I plug in P naught here, I'll get whatever value I'm getting at P naught, which has no reason to be equal to 1. Maybe it is, but why? So what this means is that I should take this and divide it by its value at P naught. By its value at P naught, I mean forget this part, which has exactly the right exponential. Just divide by the value of this expression at P naught. So I should write here, technically, theta of P naught plus sum of ui ti plus z, and here theta of P naught plus z. But this will be one of the many things I will not write from now on. Okay? You have to do it, but the formulas get uglier. For many things, up to constant normalization does not matter. If you wish, we can just declare this to be the correct normalization instead of 1, but there are problems doing that as well, because this will depend on ui and ti, which I don't want. Okay. There was a question you were asking.
About the condition of the ti, the decay of ti.
So at the moment, this is a formal statement, and this is where I was going to go. So remember in the first lecture, we were solving differential equations in formal series in K inverse, right? This is also something of the same sort, right? I mean, I was looking for solutions at some exponentials. If I have just one k here, so if it's just kt, I have exponential of kx times the series decay in K inverse, right? What's the difference between what we were doing then and what we're doing now? You would think it's very similar, but at the time I was saying there exists a unique formal solution such that blah. Here there is something global. It's not formal. This is an actual meromorphic function on the Riemann surface. So somehow I want to unite these two theories now, and the advantage of this is that this is going to be a geometric solution. That somehow if I can get functions of this sort, they're not just formal, they're actual functions. They're actual functions on the curve with an essential singularity. So I can pass from formal solutions to actual geometric solutions. The question of how this should converge, and for this to make sense, is a good question, which I will conveniently ignore, because the only case I'll deal with is if this just stops after the first 3 terms. That's the only case that we'll worry about. And then there is no issue. In general, you should study this, but I'm not going to do that. Okay? Any questions so far? So what is the use of this? The use is that I have this function psi, which depends on a whole bunch of variables, ti, right? And you can, for example, see that if I take the function psi and I try to differentiate it, I mean, this is a function psi, and I differentiate it with respect to ti, I can see what I'm going to get. If I differentiate with respect to tj, we can see what I'm going to get, right? But these functions, the derivatives of these functions with respect to ti, are functions of the same sort. Maybe not quite the same sort. I have to tell you precisely what the essential singularity at P naught looks like, but they're sort of the same sort. There is a statement you can make. You can consider the space of all functions slightly more general. This is going to be finite dimensional. And then the uniqueness will still hold. Somehow what this says is, if you have a function with a prescribed essential singularity, prescribed as generally as you want, but uniquely somehow, so the ratio of two such essential singularities must cancel, at a point P naught, and then the poles are as prescribed here, then if you do that, this function is unique. So this means if I have more than one way to construct a function with the same essential singularity at P naught, this better be the same function. This is a source of differential equations, as we'll now discover. Okay. Theorem. This is one of the many theorems without a proof. I'll use some of them, not all of them fully, next time, but I want you to try to develop some ideas about how these things are used. For any meromorphic function, E on my curve C to P1 with an nth order pole at P naught and holomorphic elsewhere, there exists a unique nth order differential operator of the kind we like. L is the sum of ui x di dxi. I goes from 0 to n, such that L applied to psi, and for psi I'll just take the one variable version I had before. So x and C P naught K P is equal to E psi of P. Okay? So X is T1. So take the version of this which I had last time, where I have just one variable which is called T1, which of course is convenient to call X because why not? So I claim that for any prescribed to me meromorphic function with a polar order n at P naught and holomorphic elsewhere, notice such a thing doesn't always exist, right? Of course, if I take a polar order a million, yes, but otherwise I don't know.
So is UI of that do not have anything to do with UI?
I'm not the greatest fan of how people have used notation in this field. So these are the capital UIs, this is a little UIs, and it's about 40 years too late for me to change the notation, I'm afraid. So these are functions UI, which are coefficients of differential operators. At the moment, they have absolutely nothing to do with these vectors, okay? Sorry.
But they will never have.
They will never have anything. They sort of will never have anything to do. But that's the expression. So what happened here? Remember in the first lecture, we were looking for eigenfunctions of formal differential operators of this form, right? And we were saying that for any differential operator of this form, you can find the solution, right? In formal series times an exponential. So this is what happens near P naught. If I just look at this thing near P naught, This is what happens. This is what I wrote, right? So near P naught, this is a formal thing. So how do I prove this theorem? So proof, idea. The idea is very simple. Use our formal study, our study of formal solutions of L psi is equal to E times psi to ensure that the essential singularity of both sides at P naught is the same. And then use uniqueness of Baker here as a function. This is one of the many proofs I'm not doing. Yes? None. I mean, I can just set all the other variables t, t2, t3, t4, and so on, just to set them to 0. That's not the last theorem I'm stating, so I'll need the other t's. Okay? This is sort of more. This is the correct generality. The next theorem will use more than one t. Okay? So again, so what am I doing here? So I have two functions with essential singularities on both sides. Of course, if I differentiate a gadget of this sort, this differentiates in respect to x. X is a parameter, right? And of course, I'll have an essential singularity. You can compute what it is. It's going to be in terms of ui's of x and times the singularity you had before. And then on the other side, you have E. E is a meromorphic function. You can expand it locally around P naught in coordinate k inverse, and you'll get the terms of expansion. You just make sure you kill all of these terms of expansion correctly. You can write this down. It's completely explicit, right? Once you've done that, you've gotten two functions on both sides which have the same essential singularity. You better make sure that it's really the same. Then you take one, divide by the other if you wish. Okay? And use the uniqueness of Baker-Heezer function. More precisely, they are both Baker-Heezer functions in a slightly generalized maybe way. Don't worry about that, right? So it's exponentials times maybe some polynomials, but not a big deal. So it's the same structure, right? So they have the same essential singularity at P naught. They have the same poles, so it must be the same function. So all you need to do to check such an equation on a curve is just check that the essential singularities are the same at P naught, because they are of the same form otherwise. Make sense? This is an explicit computation that can be discussed in exercises. Questions? Next theorem. So all the theorems I'm stating can be found in the works of Krichever. Some predate his work, but this is some kind of agglomeration. So I'm going to set here T1 is X, T2 is Y, T3 is T, T4 is T5 is equal to everything else is equal to 0. Okay? So then I'm going to look at the Baker-Heezer function psi of X, Y, T, C, P naught, K of P, right? So this is just the case when I have three variables. We'll discuss in a second why this is a useful case. So it says the following. There exists unique differential operator L1 of the kind we like in X, and L2 such that L1 psi is the derivative of psi with respect to y, and L2 psi is the derivative of psi with respect to t. Okay? I have been sloppy in writing what order these differential operators will be. They will be ordered 2 and 3. And this is a shadow of a more general result that I will also freely use. So what this says is if I prescribe my singular part here to be kx plus k squared y plus k cubed t, then I can do that. You can imagine that I can do a slightly more general thing. I could take kx, because it's convenient, plus any polynomial of k times y, plus any polynomial of k times t. The same result will hold. So in fact, if I want my exponential part to look like the exponent of kx plus q of ky plus r of k t, q and r are polynomials in k, there exists unique L1, L2, and degree of L1 is the degree of Q, and the degree of L2 is equal to the degree of R. Okay? Generalization. So how do you prove this? Well, the same way, right? The proof is again the same. It's a formal computation. This gadget has an essential singularity at P naught. This gadget also had an essential singularity at P naught, right? So if I took this, I took derivative with respect to y. Y was multiplied by k squared, so I'm just pulling out the k squared, right? Here I'm differentiating with respect to t, I'm pulling down the k cubed. Also, this is very easy to see what I need to do. So I need to cancel the essential singularity again, and I'll be done. Okay? This is very explicit. Huh? Mm-hmm. Yes. Sorry. Yes. So the coefficient does, the derivative is only with respect to x. Sorry, I was not careful. Okay, next theorem. In this generality, if this holds, then I can take the commutator of L1 minus the derivative with respect to y and L2 minus the derivative with respect to t. This is going to be 0. Okay, proof we essentially know, because remember we had a discussion in our first lecture on formal differential operators, that if I have two differential operators L1 and L2, for which psi, my formal psi at that time, was a common eigenfunction for each value of x, they must commute because they annihilate y. So proof is psi is in the kernel of this commutator. So it gives an infinite dimensional kernel, and if you compute what this is, of a differential operator in x only, because this commutator will no longer be differentiating in y or t. Okay? So this means the commutator is 0. Yes. So you have one more parameter than you have variables in differential operator, basically. Okay? So for fixed y and t, at the end of the day, there will be an infinite dimensional. For any fixed y and t, this will be a differential operator in x with coefficients functions of x. Y and t are fixed, which will have an infinite dimensional kernel, so it must be 0. If this is true for all y and t, this is true. This is true. Okay? This is a proof, right? Nothing. This is an honest proof, more or less. Right. At the level we are going today, this is clearly an honest proof. Okay. I want to do an example. So my function psi of x, y, t, in the simplest case I wrote before, is the exponential of kx plus k squared y plus k cubed z plus k cubed t, sorry, right? This is the case I was considering here. Times something, right? What is this something? So this is I'm writing the expansion, if the word expansion made any sense, of a function around p naught with an essential singularity. So near p naught, right? So this is going to be 1 plus psi 1 x, y, t, k inverse plus psi 2 x, y, t, k to the minus 2 plus dot dot dot, right? So near p naught means I'm writing this in terms of the point p near p naught, right? This is a function of p. I have stopped writing c, p naught, and k as parameters of my function. They're always fixed. So k is just the coordinate of the point p naught, right? Which goes to 0 at the point p naught. So this expansion is in k inverse, right? So that's my function psi. And you can then ask, what are the differential operators? So L1 is d squared dx squared minus u of x. I'll tell you what u of x is, minus the function u. L2 is d dx cubed minus 3/2 of the same function u, d dx, minus the function w, where u is 2 times the derivative of the first term of the expansion with respect to x, and w is 3 times the derivative of the second term with respect to x, plus 3 times the second derivative of the first term with respect to x, minus 3/2 u times psi 1. This is a computation. I can just run the machinery I've done in this form, right? I'm not going to do this now. You can try to ask during the exercise session. I hope somebody will be able to do this. I won't, because I will make too many mistakes, okay? But I copied this from Krichever's paper, and he did not make mistakes. So this is correct. What is the use of that? Okay? So what's the use of that? The use of that is, of course, I can now compute something very explicit. So what is u? U is this derivative of psi 1. Psi 1 shows up there. Psi 2 is the next term there. Do I really know them? Well, actually, yes, I do, because this function I have an explicit expression for, right? This is an explicit expression for the Baker here as a function with a prescribed form of the essential singularity at the point p naught. This is the exponential part, which will have the pole. My differentials omega are normalized to be exactly as they should be. So basically, by expanding this in terms of the variable p, which is k inverse, right, I will be able to compute all the terms in the expansion. So you can compute psi 1, psi 2, and then you will see eventually that u is minus 2 times the derivative, d dx squared, of logarithm of theta of the stuff I get there. So u1x plus u2y plus u3t plus z at 0. Okay? You can compute w as well. Now you can compute this commutate up there. You compute this. This gives a differential equation on u, i.e. on theta. Okay. You can just compute what this is, which we'll do in a second, which I'll write the answer of in a second. So the equation is going to be the following. The equation is 3/4 of u y is equal to d dt of ut minus 3/2 u times ux plus 1/4, maybe minus 1/4 u x x x. Okay. Of course, I switched to writing partial derivatives as subscripts, otherwise it gets unreadable. So we can wonder if this is a differential equation that has a name, and it does, right? So, yes, of course. Sorry, no, I'm sorry. This is t. This is x. This is x. This is x. Okay. Okay. So this is something which is a KP equation in some form. What happened? I did basically nothing, if you think about it. All I used was, all Krichever used was use the uniqueness of the Baker here as a function in a suitably souped up generalized way. When you do that, you automatically get some commuting differential operators. When you also happen to know that the function is unique, of course, the moment you write an expression for it, you can just plug it in, expand. That's what we did. So this is all a completely sort of direct computation based on the uniqueness of the Baker. Here's a function which I don't want to prove, but it's not such a big deal. Okay. Say it again? That's a question for the audience, not for me. Is that a miracle that this equation has a name? From this point of view, it's a miracle that this equation has a name, right? I get some equation. There is no reason to think that this equation would have had a name beforehand. There is, let me say a little more. So something which is not a miracle, but which I'm not telling you about yet, and which I will never tell you about properly, is the following. So what did I really do? I said, okay, I'm going to look at the case of this hierarchy when I have just 3 variables and the rest are 0. Well, this is a poor man's version, right? Or a poor person's version. I could also, allow infinitely many variables, somehow worry about the convergence issue, which I'm not going to worry about. And then, of course, instead of having operator L1 such that its derivative applying L1 to psi gives me dt2, and another operator such as applying it to psi gives me dt3, I'll have an infinite sequence of operators, right? And of course, the commutation will still hold. And of course, I can write all of this. And of course, I can expand all of this. And what I'll get as a result is, I'm getting an infinite sequence of differential operators. So I'm getting an infinite sequence of equations, right? And this is an integrable hierarchy, right? And you can see that this is going to be an integrable hierarchy. Well, then it's going to be a hierarchy. Why it's a KP hierarchy? I don't have a good answer. Does anybody have a good answer? There is no. The KP equation was known beforehand. Sasha? Yeah. So when this equation arose, it was easily recognized. Why the equation that shows up here is the equation that appears in plasma physics, and why some reduction is KdV. I mean, there is no shallow water wave here anywhere that I can see, right? That's correct. Yes.
So if you, some So in count for Buttiashvili is I don't know. I mean, it'd be great if it were explained a little better. Why did they come up with this equation? Yeah, I looked a little bit. It's. I don't know. I mean, of course, it's a understanding function of two variables, but it's. Do you know anybody knows in the literature where it's actually like a physical derivation of KP equation is done in a good way? Right, that is easy, yes. But K,
That, I mean,
yeah,
yes.
yes, but why KP? That not known to me. I'd be very curious to know a good reference for that. Yeah.
But why it happened?
Why they keep the term they keep it, so to speak? It's not.
So let me make another comment, though. So I said this was Kp, right? The KdV that was alluded to is a version when this is 0, right? So, and this occurs, and the theorem I wrote there, the simplest function, the simplest meromorphic function was a pole at one point at a Riemann surface, which is not a sphere. The sphere is boring. I should have excluded it from the start. I don't want to do it. It could be that E has a double pole. If E has a double pole, then the curve is hyperelliptic, right? And in that case, you can use this machinery to see how this will all simplify, and you're going to get the KdV, right? I'm allowed to consider singular curves. This will be limits. This is going to be a comment in 2 minutes, if I may. For the record, KdV arises in more than one place in mathematics. That's where it arises. KdV also controls intersectional theory on the moduli space of curves. It's a different, as far as I am aware. I'm happy to, if there is some comment as to why the same word KdV appears in these two places, that'd be great. I have asked before. Yes, Lynn. So here are considered the problem of the uniqueness of Baker here as a function, at least for hyperelliptic curves. What's the original motivation? What was in the air at the time that people were not afraid to compute expansions? I don't know. Maybe some people in the audience know. This predated some of the geometric stories. So, I mean, you'll see. So, I want to make one more comment in this direction. Then we'll take a 3-minute break because I think that worked well last time and I need it. And then we'll move back to flexes and we'll see how the KP arises from flexes, okay? Which will not be the historical reason because this was later, I think, okay? Theorem. Yeah, I'm sorry that I don't think I have written the word exercise on the blackboard today. And you can imagine that every theorem I state is an exercise. I don't think this is a doable exercise. But these are topics for discussion. This is due to Krichever. You're welcome to take Pasha's class. No, I mean, so you can do in this computation is a perfectly doable exercise. There is no question, right? So starting with finding what the L1 and L2 are from the definition is certainly doable. Computing the commutator is certainly doable. Computing the expansion is certainly doable. So all of this is doable, but maybe takes a bit longer than 20 minutes if you have never done this before. If you wanted me to do this now in the next hour, I'll make 25 mistakes. It will not work out probably. But, and is much more doable, right? But I mean, you'll be able to compute the commutator, right? It's interesting to me to point out that this somehow goes back to the theta function because that's where I'm going, right? And for that, you need to compute this. And there are many ways to make mistakes in that. I think I do. I mean, in most computations, people set P naught to be 0, right? Because there is some freedom I have in this whole story. I don't really need P naught, right? But I haven't yet made that comment. So, okay, let me make this comment. So I don't really need P naught. What is Z here, right? Z was a divisor D. So D was a degree G general divisor. So this is now a general point of the abelian variety. Of course, if I have some equation which is satisfied for a general point of an abelian variety, then it's satisfied for every point of an abelian variety, right? So notice the divisor D I was choosing freely. And this was going to work for all D, right? So this works for all Z, right? And this is the derivative of this function evaluated at Z. Even though Z looks to you like a variable, perhaps, Z is an arbitrary point of an abelian variety. This is the Abel-Jacobi image of the divisor D inside the Jacobian, right? And I said take a general point. And then basically what happens here is that G's symmetric power of the curve C surjects onto its Jacobian. So every point of the Jacobian is written as a sum of some G points, and generically this is what I want. So I don't really need P naught here. And I did want to emphasize eventually this is an equation that's valid for all Z. Okay? But I plan to do this half an hour later. Okay?
Make a remark that this equation looks very complicated, and more so if you include all the lines. But it's actually so in representation theory, when we study Grassmann, it's not about linear relations, it's defining equations of Grassmann. So if you do it with infinite dimensional Grassmann, these equations are actually exactly.
You should learn that.
You can read it in the book of Carson, right?
Yeah. Well, there is an algebra geometric viewpoint on this from the infinite dimensional Grassmannian, which I'm not mentioning at any point.
People want to read about the path of Jacob, and
that's a that's an excellent book. That's really down to.
Yeah.
I think Andrei Dashek is teaching the course this semester on distance. And as usual with beams of courses, you have notes available, videos available, or should have, on beams of
and while we somehow added, so this is the point of maybe one of the points of Jacob was that you're right. You have a quantum integral system. You take expectation of that and you get solution of velocity. And there's a quantum integral system that underlies things like Cauchy integrals on modular curves. Take that to think you take two.
I'll ask again once I'm not at the blackboard. Okay. 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 We're reasonably okay. Yes. Any curve C. For any curve C, for any parameters x, y, t, for any point P naught, the same. Oh, well, I mean, what do you mean the same? U is this derivative of a theta function of that curve, right? The theta function knows which curve we're taking. But the formulas are exactly the same. Okay? That somehow, the whole machinery is completely formal and universal, right? So again, the point is, at the point where I have essential singularity, I'm doing some formal computations, which are just completely formal and see nothing. But then since I'm on a curve, these formal computations and uniqueness tell me I actually have constructed something geometric. That's what happens. I want to state the last theorem for this section and take a 3-minute break. This is due to Krichever. So it says the following: for any differential operators in one variable, L1, L2, which commute, there exists a curve C. I can tell you what this curve is. This is a C is the curve given by differential by the polynomial equations satisfy. There are going to be caveats here, but yes. So they should be GCD of order of L1 and order of L2 is 1. The prime example for me are orders 2 and 3. There is a version when the GCDs are not 1. It's a bit more elaborate. This is the equation satisfied by L1, L2. So we learned in the first lecture that there was that if I have two commuting differential operators in one variable, they satisfy a polynomial equation, right? So this is polynomial equation. We learned this. So that's what the curve is going to be. There exists a curve C, a point P, node, which is just the point at infinity, and K, which is the coordinate near that point, such that the corresponding psi x C P node K of P is a common eigenfunction of L1 and L2. Okay? So if I have a pair of differential operators in one variable of the form we considered the first time with co-prime orders for convenience, which commute, we learned in the first lecture or two that they must satisfy a polynomial equation. That polynomial equation defines for me a curve C in C2. This is not a compact curve because it's in C2. Our setup was compact curve, so I need to compactify it. If I compactify it, I imagine points at infinity, and we have to fight whether we're going to go to CP2 or CP1 cross CP1. If I am adding points at infinity, you have to ask how many points I'm adding at infinity. And you are actually going to check that you're adding 1 point at infinity. But it's a singular point at infinity, which basically has n branches coming together. If you separate the branches, k, which is the nth order root of the coordinate there, so it's really k is sort of z to the minus 1 over n, where z is the coordinate near infinity, okay, will be the local coordinate on the curve. I have basically told you a proof. You need to check that the number of branches is correct. You need to check that this is a local coordinate. And then you need to check that the corresponding psi will be a solution of L1 and L2.
So the curve does not have to be smooth, but the point is
The curve C here doesn't have to be smooth. The point I imagine at infinity is not smooth, but what I'm really doing is I'm taking the closure of the curve C in CP2, and then I'm taking the normalization at infinity of this closure. And that's going to be smooth at infinity. This is going to have n branches at infinity, distinguished by the values of the root, which you can see from the description of the eigenvalues near infinity, which I'm not doing. And then you're in the setup we have. So the curve is really not smooth. So the correct generality for Baker-Hieser functions, it doesn't matter so much that the curve is not smooth. The curve as a point P node better be smooth because I'm choosing a local coordinate at that point, and I better be able to do that. But this goes beyond our scope. What is a singularity at infinity? It's n branches coming together. So that's a Baker-Hieser function, exponential singularity. I mean, so has this singularity of the Baker-Hieser. This is a Baker-Hieser function, right? So in the first lecture, we discussed that if I have L1 and L2, the formal differential operators commuting, they will have common eigenfunctions, blah, blah. This now says there is a geometric construction of some eigenfunctions. Okay? I am not saying these are all the solutions. No, 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 no. So what this tells you is that if you have a pair of commuting differential operators in one variable, you can find solutions of them, common eigenfunctions for them, in this geometric form coming from curves. Okay?
And in fact, the closest is to Newton's theorem on the top sector board, right?
Right, and this, yes.
So this theorem tells us that there is a common
So, yeah, so, yeah.
C minus B0.
So, yeah, so altogether this establishes bijection between pairs of commuting differential operators, which we know. The orders are co-prime. I erased it because I ran out of space. Yes, which I did before you came, right? So Birchnell challenge I proved in the first lecture. So the orders are supposed to be co-prime for this to hold. Otherwise, you have to modify the statement somewhat. I will ignore this issue. Okay. For me, the only case that matters is orders 2 and 3, which are certainly co-prime. Okay? The issue of singularities of the curve C I will also ignore. I'm aware, yes. I'm aware. We don't need this. I mean, I'm skipping this. This is, epsilon squared term and the things I'm cutting off, yeah. I know, but there is no way to explain this. Okay, so this is basically a bijection between such curves and commuting rings and rings of commuting differential operators. I don't want to make this a precise sentence, but that's what it is. Okay, upshot. First, we have a break for 3 minutes and then come back. Second, we know how to construct some geometric solutions, periodic in some sense, if you wish. Finite zone words, there are many words, which I'm not saying, of pairs of commuting differential operators starting from curves. That's what we've learned so far. Okay? So remember, there was one story. The story was about commuting differential operators. There was another story about curves. In the story about commuting differential operators, first it was a formal story. Now we've found actual solutions. In the story about curves, I've learned how to construct Baker-Hieser functions. This is a story we developed here. Separately, I learned how to think about the Jacobian. I've developed trisecants of the Jacobian and all that, right? So I want to complete that side of the story in the next 20-something minutes to tell you that you are going to get the same KP equation, so it will not look the same when I write on the blackboard from that story. Okay? 3-minute breaks. 3-minute.
Theta must be replaced by alpha, and then it is exactly like Victor H and many others. So, but there is special direction, right? If we were doing this direction, which is algeo, fine zone, quasi-periodic.
Which are all the words I think I said in the last 3 minutes, right? The story I'm telling is not connected to Kac-Moody. There are wonderful generalizations to infinite dimensional. This is not the direction I'm going. Okay, so a 3-minute break. Пока нельзя. После лекции, извините. Мне надо хотя бы подумать, что я буду теперь говорить. No, after the lecture, please. I mean, this is a break for me as well as for the audience. Sorry. Извини. Спасибо.
Пока стирал, пленки придумал.
Ну, вот это он придумал, когда стирал пленки. А что он придумал, когда он кастрюли мыл? У него было 2 истории. То есть, это он придумал, то есть функцию Бейкера-Хезера он придумал, когда стирал пленки. Я, конечно, что-то другое рассказал. After the talk, please. Not when I'm taking a break for 2 minutes. Yeah. Not when I'm taking a break for 2 minutes. All questions after the talk. After the talk.
Русские приехали в Китай разговаривать по-английски.
Ну, нормально. На что? У вас жизнь такая, я понимаю. Does this work? No, this works. Okay, so let's continue maybe, if that's okay. So first of all, the history of how this was discovered, and you should ask Alexander Veselov for more details, was that Krichever did the hyperelliptic case of much of the constructions. That's why the functions are called Baker-Krichever. Baker had some ideas in homogeneous. Then this was done by Itz and Matveyev in more generality or almost full generality. And then this was done by people around Novikov, Dubrov, and Krichever, and the school, and so on. The full statements I'm writing, I think, are due to Krichever at the end of the day, but many steps have happened before. Okay, so now I want to go back to the story about Kummer varieties. So recall that we have the picture, which I'm sure was on the blackboard right here yesterday, right? This was the projective space with dimension 2 to the g minus 1. This was the Kummer image of a Jacobian of a curve. And then there were many trisecant lines of that gadget, which looked like that. Under some degeneration, they look like that. And on the most degenerate case, they look like that. Okay? This is supposed to be a point of multiplicity 3. What were the actual trisecants we wrote? We wrote the following trisecants. The Kummer image of, I will ignore over 2 because my writing just gets sloppy. So the Kummer, the trisecant was this statement. I write wedge, thinking of this as points as c to the 2g, and then wedge means wedge. So this is to say that 3 points are collinear, right? There was over 2, I'm ignoring this, which I shouldn't, but which I'll regret eventually, but not yet, okay? So this was a trisecance. This was a 4-dimensional family, 4-parameter family of trisecants of the Kummer image of every Jacobian variety, where you recall that for any abelian variety, the Kummer map embeds the quotient of an abelian variety by plus minus 1 into a projective space. So in particular, the signs, the overall sign here doesn't matter. Notice this is very nice and symmetric, by the way, right? I didn't need to look at my nose to write this for you, because I know how it should look. This is all in peak node. So I have 4 points. I just take 2 with a plus sign, 2 with a minus. Somehow it's all very natural. No choices really made. So this is the most general trisecant. How would I get from this the degenerate versions? Remember, we're trying to go for the flex lines, right? So I'm going to take a limit, and now I'll look at my nose because otherwise I will not compute correctly. So I'll take a limit as S goes to P. Okay? So these are 4 points on the curve. I can choose arbitrary points. I'll just move them. Notice that these points are the sums and differences. So what we are doing now is an elementary computation of how these points depend on this. So if S goes to P, it cancels here. I get Q minus R. If S is P, this cancels here. I get Q Kummer image of R minus Q. And here I get the Kummer image of, well, this is 2P minus R minus Q, right? Of course, if I just take the limit, I get this is 0, but that's boring. That's just vacuous, right? Because this is the Kummer image of a point. That's the Kummer image of minus that point. So these two things are just equal. Of course, if I have 3 points and 2 of them are the same points, they lie on a line. That's not a particularly interesting statement, right? So I need to take derivative. Need to take the next order term as S goes to P and expand, right? So what am I going to get here? So here I get Q minus R plus somehow the infinitesimal P minus S term. Here I get R minus Q minus the infinitesimal P minus S term or something like that, right? If I do this correct. Sorry, also plus, but if I flip the sign, it will be with a minus. So what I'm going to get is the following statement. So basically what I said is I'm taking S to be P minus U epsilon. That's a capital U. It's a vector U, right? So what this gives me is Kummer of Q minus R plus U epsilon, Kummer of R minus Q plus U epsilon, Kummer of 2P minus R minus Q. Here I'm going to drop the minus U epsilon is 0 because this certainly has a nice limit. I don't need to worry about that. Okay? So that's what I have. Now I expand. This is a function, yeah, this is a vector function, who cares, of this. This is a vector function of that. They equal, so I just try the expansion, right? So what does it mean? So I have this guy, and this is a small perturbation of this guy and that guy, and they are 3 collinear. So this means this thing itself, the limit, plus the perturbation, and the third guy is supposed to be collinear. So the limit, as epsilon goes to 0, implies the following statement, that if I take the Kummer image of Q minus R, and then I take the derivative with respect in direction U of the Kummer image evaluated at Q minus R, and I take this, then this is 0. Okay? This starts to look a bit ugly. I will want to set P equal to 0, because when I'm taking the map from C to its Jacobian, I know that I'm going to pick 1. I really want to go to pick 0, so I'll just say P is going to go to 0 when I'm thinking of as a Jacobian of pick C. So I want to take the limit again. Now take the limit as R goes to P. Okay? And let V be the second order derivative of the Abel-Jacobi map, Abel at P. Why am I saying this? Is because actually if you figure out what this U is, this is the first order derivative. So the vectors U and V are the first and second order derivatives of the map that sends C to its Jacobian. What is U? So U is the first order derivative of this map. How is this map defined? So the map that goes from C to its Jacobian, I told you about this in a very abstract way. I said, well, this is C. I identify this with peak 1 of C, and I'm happy. There is a much more explicit way. So I can choose omega 1 through omega g to be a basis, a normalized basis of holomorphic differentials. And then what this map does is it just takes an integral from the point P to a point Z of omega I, right? So Z maps to this point, right? Because I've started my Abel-Jacobi map at P, so it means P goes to 0. So that's the map. So it means U is just the vector of omega 1 of P to omega g of P. This is not well defined, right? These are values of differentials, but as a point of the projective space, which is really all I care about, this is well defined. And similarly, the second order derivative are the derivatives of this, which are quadratic differentials at the point P. Okay, so if I do that, what I get is something like this. So I get the Kummer image of Q minus P minus U epsilon minus V epsilon squared. I'm computing honestly the expansions you're going to get here. Du P plus U epsilon plus V epsilon squared minus Q, which is a Kummer image. And I have written this with a P, but anyway. Right, so in this formula, I haven't yet substituted P equal to 0. But just look at this. This is just completely explicit. And I can just expand it. Expand, and this is an exercise. Exercise is to say that the lowest order term, the lowest order non-trivial term, is the following. It says the Kummer image of Q. So here I've set P equal to 0. Wedge the derivative with respect to U of the Kummer image of Q. Wedge the second derivative with respect to U plus the first derivative with respect to V of the Kummer image of Q is 0. Okay. For any Q in C. Okay. What is this an equation of geometrically? So this is an equation to say that we have a flex line at Q, right? This is an equation that guarantees that I have a flex line at Q. Maybe I still don't like this equation. It's not a differential equation yet. I'm taking Kummer image at Q, right? But now I can take the limit. So this is an equation of a one parameter family of flex lines. So as a point Q approaches P, which is 0, this is a flex line at the point Q. But now I can take Q expand, Q goes to P, which is 0, right? And I can expand this, I mean, this, in Q to all orders. Okay? Why not? So the lowest order term is going to be an exercise. Lowest order term is the following. P at 0 is 0. Okay? A word of caution that please ignore. As you remember, 0 is a point where the Kummer map is singular, I'm aware. And so the first order derivatives will vanish by parity. So will the third order derivatives. This is why you only see second and fourth order derivatives. This works out well. Some constant. And U and V I've told you about before, and you can make an educated guess as to what W is. This is going to be the third order derivative of the Abel-Jacobi map at the point you've chosen. Okay? If you have a hyperelliptic curve, and if you start it with a Weierstrass point, this will disappear. The equation will become simpler. Okay? I'm not going to write this. Exercise. So this is an explicit differential equation for the Kummer image. I can now use Riemann's bilinear relation to convert this, to deduce from this the KP equation, right? Not quite true. The lowest order term equation for the theta function itself, for the usual theta function. Okay? I will leave it at that for the time being.
So this gives another proof of the fact that this function satisfies KP equation.
Almost, not quite. This is not the KP equation. And this is what I wanted to explain without a proof, because this is a computation. This is precisely what I want to explain, but in words without a proof. Testing, testing, testing. Okay. Okay. Thank you. Okay, just a couple minutes to go. So the theorem is, if I have a principal, a polarized abelian variety, and I have a curve inside this abelian variety, I'm writing it this way to convince you this is not the strongest thing you want. And you have 3 points, which I'll allow myself to denote.
Yeah, the problem is for the Zoom translation. That's why you kind of
So how about now? Can you hear now? Yes. Okay, let's be very careful. Maybe I should do this. Okay? Okay. Okay? Okay. Okay. So if I have 3 points, maybe I shouldn't even denote them Q, R, and S. I'll denote them something else. So let's denote them. They are related to Q, R, and S, but they're not the same. So Z1, Z2, Z3A, such that I have a family of trisecants. So Kumar of P plus Z1, Kumar of P plus Z2, and Kumar of P plus Z3 are collinear for any point P on the curve C, then A is a Jacobian of C. That's what the result of Gunning really is, if you look at it carefully. So this is somehow weaker than a solution to the Schottky problem because the curve is really given to you. Because you have a one parameter family of trisecants, which are all obtained by translating each other. The proof of this goes via the Matsusaka-Run criterion. I'm not going to tell you anything about that. I'm not even going to write what this is. It's a beautiful result, beautiful proof. Matsusaka-Run criterion is also a beautiful result with a beautiful proof. Not so hard in retrospect, but in a different direction from where we're going. You can have a souped-up version. Theorem, this is due to Welters, essentially. It says, again, you have A, you have a curve, and then if the Kumar image of P plus Z, I mean, Z in A is fixed, E is a flex point for any P, then the abelian variety is again a Jacobian. Okay? And the flex point, you know what it means. It means that condition, if you wish. So again, this is a beautiful result. Doing this, given this, requires work. Not trivial at all. But again, you start with a curve. Next theorem. An infinite dimensional formal germ of a family of flexes suffices. An infinite order, sorry, not infinite, infinite order. So here I said, if I have an actual curve which parameterizes flexes of the Kuma variety, then the abelian variety is a Jacobian. Here I'm saying I don't really need to have a geometric curve. It's enough to have an infinite order germ of a family of curves. This you might want to believe on general principles because we are somehow in an algebraic setting. So an infinite order expansion should be good enough. Anything formal should be geometric. This is not a proof, but can be made into a proof. I want to state the next thing, okay? Which is due to not clear. Well, I know who did the next one. How about that? So this is 1980s, early 1980s. Any G, there exists a number n, which depends on G, such that an nth order formal germ of a family of flexes characterizes Jacobians. Okay? So this is the next step. Instead of an infinite order germ, for each G in each complexity, you only need finitely many terms. Okay? This n is not really explicit in their paper. And it certainly grows horribly the way you just look at what they do. Doesn't matter. What this says is that having a finite order germ of a family of flexes suffices to extend this to an infinite order germ, and then this suffices to extend this to an actual curve. That's how the logic goes, right? Okay. Huh? Yes, of course. You just need to phrase it. I mean, so they certainly explained this, right? I think this was sort of in the air at the time. That's my understanding, but I'm not sure. Okay. We're almost there. I mean, we are out of time, so we are almost there. So I'll just say a few more words here, and then we'll be done. Arborello and De Concini do more than just this, of course. This one? This one's here. Is this a theorem of, is this theorem to, which one is theorem 2? This one? This one? Noetherian. I mean, yes, I agree. But yes, I mean, going from here to here is not a big deal. Okay? I'm trying, I need to build suspense, okay? This is theatricality, not mathematics. Okay, next theorem. So this is a conjecture. This was a conjecture of Novikov and the theorem of Shiota. For any G, the existence of a 4-order germ of a family of flexes suffices, characterizes Jacobians. Okay, and this is the KP equation. So the infinite order germ is the KP hierarchy. This is the KP equation, the KP equation. So the KP equation is not what I wrote. It's the existence of a fourth order germ of this thing. So you can expand this and see what this happens, right? So why would you possibly believe this morally? Because somehow you want to, of course, what you want to do is you want to start from a fourth order germ and just keep ratcheting up the order of the germ you get, right? And at each step, there'll be some abstraction to extension of some sort and whatnot. But the jets bundles are extensions of each other. So you somehow might want to believe that if you can solve it first order, you will then be able to solve it second order. Jet 2 is an extension of jet 1 by jet 1 or something like that, okay? This is morally what you would like to believe. This doesn't mean you can really prove something in 2 lines doing this. This is a famous theorem, okay? And then this is the entire KP hierarchy. So this is the KP hierarchy. So this is a statement that the KP hierarchy characterizes Jacobians of curves. As far as I'm concerned, from this point of view, KP hierarchy is just a name for higher and higher order expansions of the flex line. Okay? So, and lastly, the conjecture due to Welters and the theorem of Krichever is that the existence of one flex line characterizes Jacobians. Okay? Notice that this somehow, from this point of view, there is a disconnect from here to above. Because if I know something that I have a jet, I can try to extend the jet. Here, I have no jet of a solution. So the way you would want to prove this, of course, you would want to prove that there exists a higher order jet, an infinite order jet, an actual curve of flex lines, and then you're done. But you don't here know where to start, right? In what I was doing here, I was conveniently taking limits. There is nothing to take a limit of if all I have is just one flex line. Okay. So this is the goal of tomorrow, and we're already well out of time. So thank you.
Okay, since we're planning to do the group photo, maybe if you have any questions, come to the discussion session and talk to them then, or ask them tomorrow. Okay? Now the hope is we go out, and people will tell us where to go and how to stand.